format is 6 and it goes up to 2 decimal places. So that's about the parameters of the information you can fetch from fetch file, the initial information. Like, okay, I'll discuss these. Okay, so next is header. So header is like kind of a preface of its file. You can get the most basic information about that specific observation. All right. So here, wait, let me run this. Okay, yeah. So first we are fetching the header from header. I like this function. Header equals to HDO list, which we got here. Okay, so we are fetching the header of that fetch file, and from header we are fetching object, telescope, and data information about these things. In header, there consists of like different information you can fetch. And okay, all right, sorry. Okay, so yeah, in header we can fetch with different kinds of information. So with right now we are fetching object, telescope, and date of observation. So these are our fetched information. And then there's history key. So what history key is, it's like a process, like record of the process which has been done on this fetch file, and it has been modified or overwritten, like what are the things which have been done on this fetch file. So you know what the initial thing was in fetch file and how it has been modified. Let's say multiple people processes the same fetch file. Some person one did something, and person two didn't know about it and did the same thing. So a multiple person can process the same kind of thing in like multiple ways. So there will be a lot of history keys. So we don't really want to see all of it at once. And to avoid that, we like kind of plug us index that we only want to see last three entries, or whatever you can handle, or whatever you want to observe about that fix file, that last three, whatever modifications has been done on this. So that's what history key contains. And since this is the most basic file, it does not contain any history. But for example, just to show you guys, this is what the history will look like if there is in any actual fits file. Um, Wait, I'm not seeing any questions. Wait. Let me check. Okay, no questions. All right, I guess we'll keep proceeding then. Okay, that was about history key. And yeah, like history key is kind of important to observe, as you'll know. If the fits file has been changed beyond what it was originally, and if you want to work on it, or you want to trust that specific instance of its file. So yeah, next is the data which we will extract from fits file, right? So these are the basic kinds of data which we'll extract, the data type of it and the shape of data. All right. So class is all right. So ND stands for n-dimensional array. Arrays can be of various dimensional when it's like expressing an image. We'll see later the dimension for that image which will be proceed will be around, I don't know, I don't remember. All right, we'll see that later. So like these are the basic information we want to fetch before working on that fits files. All right. The shape basically defines the dimension of the data. All right. Image data. All right. Yeah. So thing is, we are first visualizing our this fits file. So we are talking about the image data only. That's why I'm talking about pixels and its dimension. Next is basic statistics. All right. So about the basic statistics, before you want to visualize your image, you want to think about, let's say you are observing some celestial body which has very high brightness. All right. And there's a celestial body beside it with very low brightness, almost negligible, very faint. So to keep such things balanced, we want to get an idea of what we have in data. So for that, we'll fetch the maximum value which we have in image data and the minimum value. All right, and mean and standard deviation. Right, I'll add one more thing. Like, why are we doing this? Like, why are we fetching maximum, minimum, mean, and standard deviation? Right. So let me add some comments. Minimum is for, wait, minimum, maximum, minimum, mm, mm, standard deviation. All right. Minimum, maximum, standard deviation. Yeah, these are the four statistical observation we are making. Right. So minimum, what we can like deduct from the minimum value is the background noise of this image, like the faintest brightness, I guess. Mm, noise. We are with maximum, we are fetching the brightest pixel in image. Right. We are with me. We are kind of concluding the average brightness of the image or the sky or whatever you were observing. Mm, sky brightness. All right. With standard deviation, we are observing the noise level in that image. So that's the reason for fetching these statistical values before visualizing the data. So let's plot the data without um implementing these statistical changes. Mm, First, to see the difference. Mm, All right. As you can see, I have linearly scaled this image. Like I have not changed anything. What you are seeing is the raw data, image data, which we fetched earlier. Mm, Image data, image data, image data. Right. Yeah. So this is the raw data visualization. It's black and white. It's like it doesn't really make sense when you wanna observe things on smaller scale. And for that, we'll be making certain changes, which is log norms, which is next. All right, yeah. So why it looks bad, obviously, which I mentioned, when there's a faint celestial body or whatever you're trying to observe, which is faint, and it is next to a very bright celestial body, we won't really be able to visualize or even detect it. So for that, to detect it in our image, to clearly visualize it, we have to scale this thing uh, close to what human eye can perceive. All right, so that fixing is known as logarithmic scaling, and the function for it is log norms. Wait, let me check for questions. Okay, still no questions. I guess I'll discuss some basic questions which I can think of myself at the end. Because it is important. I'm not sure if you guys are understanding it or not. Mm, all right. Hmm. Okay. Yeah. So next fixing is logarithmic scaling. Mhm. All right. So whatever we plotted earlier, it was like very vague, very faint, very unclear. So next is logarithmic scaling. And for that, see the parameters here. we use the image data, which was the old parameter, all right, which was not scaled. Now we'll apply a function called log norm, which scales our parameters like in a logarithmic way to get a better understanding of what's on the image. Oh, yeah, all right. So you see, that's how image looks after logarithmic scaling. You see the difference? Let me show one difference. All right. Okay, so all right. For test, look at this top corner here. In earlier linearly scaled image, you can't really spot something, like you can barely see anything. You won't be able to spot anything. But in logarithmic scale, you can see two bright spots, somewhat faint, but still detectable. But earlier, it was barely even visible. Right. So that's how logarithmic scaling fixes our visualized image. All right. You guys understand these labels, right? I don't have to explain these. These were covered yesterday. Okay, still no questions. I mean, at least can you guys type yes or something? And not in Google Meet, actually. I'm not able to see that in Discord. Mm, all right. If something's unclear, please do like interrupt me. Mm, oh, I was saying the wrong channel actually. What telescope is this from? All right. It was fetched here. Yeah, these kinds of information are in meta, like a header. Do we have spectral data for this? No. Actually, I imported another FITS file for spectral data analysis. We don't have spectral data for this one. All right. So I guess that covers visualization. I mean, it was pretty simple. These next stuffs are a bit complicated. The theory behind it, actually. All right. So next is world coordinate system. So we talked about what we are looking at, and next we'll be talking about where are we looking. All right. So when talking about where, uh, for Earth we have latitudes and longitudes, all right. But for sky, we have something called RA and declination. RA stands for ascension or something. Wait. Did I cover this? Wait, I have to explain this, right? All right, no, it's fine. Yeah, right. Okay, it's the world coordinate system. All right. So world coordinate system, we'll be talking about where we are looking at. Yeah, obviously. So the two parameters which we use are RA and declination. RA stands for right ascension and declination is, I will explain those two parameters obviously. So RA is right when an object is overhead to the pointing, like where the exact pixel where the telescope is pointing, and RA is recorded when that spot is overhead to the specific pixel we are talking about, which is the next parameter which I'll discuss. So that's RA, or we can simply think about the horizontal spacing kind of. It can be measured in two units, hours and degrees. And when RA is zero, essentially what we are having is that I have to explain one parameter before I can discuss this. So I'll come to RA again. Before that, I'll explain declination. All right. So declination is like angular distance of an object, right? In like north or south kind of. That's declination. It just talks about the vertical coordinates kind of. That's declination. Um, the parameter I was talking about is celestial equator. Celestial equator is like the center of where we are observing. So, with respect to the celestial equator, the north and south are the declination, and the time or the degree at which it comes overhead with the celestial equator is RA, right ascension. All right. So these two are the basic parameters which we will be covering. All right. So to fetch the world coordinate system of any fetch file, or we use function WCS, and I'll discuss the whatever the output is. All right. So we got two axes, which is obviously the RA and declination. The coordinate type. All right. So coordinate type is we measure RA and declination in we can measure it in various systems. Like the one system we are using right now is like how do I connect this? There are like seven. No, I forget. We will just talk about the system we are using right now. Okay. So the current system which we are using is the tangent plane projection. All right. So what it does is it flattens a small patch of the sky which we are observing, the curved sky, a small patch of it into the flat detector. That's how it converts the coordinates. So that's the coordinate which we are using, tan. Tan is tangent plane projection. All right. So that was C type, and next is C units. Both are in degrees, but as I mentioned, RA can be measured in time as well, which I'll plot later to show how exactly. All right. Next is CR val. So CR val stands for coordinate reference val. So these are the reference sky coordinates. Like it talks about a specific pixel that sky coordinates of this pixel is this RA and this declination. And this is like center of our telescope. Like it is the center of whatever we are observing through our telescope. Okay. So next is CR pixel. So CR pixel stands for coordinate of pixel, and it is with reference to CR val, and let's say using that reference, like kind of relative to it, we like locate some pixel with it at CR pixel. So there's one interesting observation here, the large value in negative. So what this one suggests is the CR pixel of the one pixel we are talking about is outside of this image. So what we can deduct from this is this image was a part of larger image, and this specific instance, the image has been like cropped to a level that we have like a very small fragment of that initial image. That's why we are getting this negative data. The initial point was way outside of what we have. So that's what we can deduct from this negative value. And PC11, PC22, these, as you can see, we have four parameters. So what we can deduct from this is it's a matrix. All right, it's a matrix of pixel coordinate matrix. That's what we call it. We can make a matrix using this, and this kind of encodes rotation of image on sky. Like what you can say is image was not perfectly aligned. Obviously, there will be rotation in whatever you're observing because of Earth's own rotation and some other factors like your detector can be tilted, telescope can be tilted, or whatever. So to fix that, we have pixel coordinate matrix. All right. So next is C delt. So C delt stands for coordinate delta. It is the pixel scale. The two you see these two parameters. These are talking about the pixel scale and degree or arc second per pixel. That's what these two parameters are talking about. So that's that. N-axis is the dimension you can get from this image, which is like we saw this earlier as well. Mm, 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 mm. Yeah, here 893 and 891. These are the dimensions of the image which we are observing. So that's the same thing as earlier. All right. So that's about world coordinate system, I guess. Next, we'll be plotting it. As I mentioned earlier, how we can exactly plot this array in hours. So this is how it's like divided when we visualize it. So instead of degrees, we talk about the duration from when it comes to overhead with the celestial equator. So that's how the hour or time unit of right ascension is used. And obviously, we have our declination here. Mm. Wait, let me check for questions. Mm. What are the other kinds of projections? Damn. Do I really have to discuss that? It's kind of a lot. I couldn't use all of it. Mm, what else show, I guess. Mm, Samantha. Mhm. I'm just fetching an old link. Just wait. 3 minutes. Hmm. Okay, now this one. Oh wait, my window is invisible. Is that something else? Hmm. Well, it's taking some time to load. Okay, forget it. It's taking too much time. Uh, mm, right. Okay, so we are back again. So about the coordinate systems, I wanted to show you guys the different the FITS file in which they can be downloaded in different coordinate systems, but well, bad luck. So all right, so different coordinate systems, like there are like 7 to 8, I guess. Uh, like conic projections, cylindrical coordinate system, and systems like that. Yeah. But seriously, I don't think I would be able to discuss all of it right now. I mean, I myself didn't look all of it yet. Okay, so there goes Shiv's question. And next is Abhinav's question. All right, so how exactly are the pixel coordinates changed to array declination coordinates? Okay, so if I understand your question correctly, you are asking about how the WCS function exactly works, right? Hmm. Did I get it right, Abhinav? Just to clarify the question. It is it? Mm, okay. Alright, so I guess I'll skip that. But still, uh, from what I understood, we can look at the documentation of WCS sub package of what it does exactly. But yeah, it involves a lot of transformation matrix and all that stuff, which are like very deep down theories. I don't think I'll be able to cover that today. Mm, all right, so I guess that's all for it for now. Okay, we'll be moving ahead then. Okay. Mm, all right, that was done. So now spectral data analysis. So the reason exactly we do spectral data analysis is to get the wavelength and flux of kind of data, not really to visualize it, but to analyze what kind of what is made of what we are observing. We talked about how it looks. We talked about where it is. Now we'll talk about what it is made of. All right. So that's spectral data analysis. And instead of doing all it in different blocks, since we are already familiar with all the functions, I have put all of it in single function and I'll just plot it at the end. And yeah, for this spectral analysis, I'm using a different file, this one, because as someone asked, the earlier file did not have any spectral data. That's why I had to use the another one. Okay. So for spectral analysis, I'll be mostly talking about its output, how to read it and stuff like that. Um, okay. So as I mentioned earlier, spectral analysis is not to visualize. I mean, it could be, but not usually because we are only going to talk about the wavelength and flux. Okay, so the primary row of it is empty here as well because there's no image data. All right. So next we'll be talking about HDU1, the first row, second row, HDU1. So COADD, it stands for co-added data or co-added spectrum. All right. So in spectral analysis, the single exposure, like it is too faint or too noisy to conclude anything. So we kind of like co-add a lot, like more of it to make it make sense kind of thing. So that's COADD. Um, that's what the first HDO one covers. And as we can see, it has 139 cards. So like 139 different instances of observation. Uh, sorry, 139, 26 cards. Sorry, 139 was for previous one. It contains 3,808 rows. So what the rows in it contains is the wavelength bins. And for columns, the 8 columns have different physical quantity of that whatever we are observing. As I said, we are talking about what it is made of. So we have to talk about its physical properties, right? So these physical properties could include properties like flux, properties like let's say the model which fits best for this, properties like masks and quality flags and some log of lambdas, like it is log of wavelength basically, a log base 10 wavelength. And I think that's all, I guess. Okay. Mm, right. Sorry. There's one more property, the noise. Yeah, noise. Okay. So next we'll be talking about the spec object. So spec objects, like it is the main object we are trying to observe or study, right? So this row contains one more thing about the previous row. The properties which I mentioned, we can deduct like those data can be used for redshift movements, emissions, absorption lines, analysis, and like galaxy classifications as well. So that's the use of HDU1 row. Okay. So next is spec object. Basically, HDU2. Okay. So it talks about the spectral object and it contains the derived properties of object like mm, what it like the properties which I talked earlier, right? For redshift, for galaxy classification, star classification, and properties like velocity dispersion, line strengths, quality flags, these kinds of properties. That's what this spec object talks about, spectral object. Right. Uh, okay, so this one contains 262 cards. So 262 different instances of data. It contains only one row because we are observing only one celestial object, right? We are talking about spectral objects. So obviously there will be only one which is emitting these. So there will be only one. Okay, so that covers HDU2, I guess. Mhm. All right. So third, HDU3. So this row talks about the line measurements, basically the catalog of spectral lines which we are observing, kind of. So the row contains the identified emissions, right, or the absorption lines. Okay, the examples could include H alpha, H beta, and such kind of spectral lines. All right. Okay, so also one more thing is when you see this specific row, it also confirms the redshift moment, okay, and chemical diagnostics and star formation and stuff like this. It confirms the like it is there. That's what this specific row talks about. Next is HDU4. Like there are a lot of up there. There's up to 11, right? So it's up to 7. Think. Right. For HDU 4 to 7, it talks about the blue camera. This and HDU 8 to 11 talks about the red camera. So what these are is like uh, separate like kind of detection for red and blue wavelengths. Right. Mm. Okay, yeah. So also one more thing. Its row talks about the calibration exposure. Hope that makes sense. So that's the plot we got. Wait, I'll check for questions again. I think I wasn't really clear about this specific part. Mm, do you guys have any questions? What is the default catalog for spectral lines in HDU3? Can we change the catalog use? Right? Mm, I don't think I understand your question clearly. Default catalog? What do you mean by default catalog? Measurements of specific wavelengths. Okay. I mean, obviously, it can be changed. There's no doubt about it. That's for its editing. In today's session, mostly what I'm covering is like how to read the FITS file, not the editing part. Because for beginners, I don't think editing is needed. First, they gotta like read the FITS file, deduct things from it, and then they will reach a certain level that they have to edit things to make things easier for themselves. I'm not covering editing part today, actually. All right. Mm. Oh, all right. So I guess that covers it. So right. Mm, so whatever observation you made, there's a small tweak of example I'll be sharing to at least make you guys familiar with how editing is done. As I'll be taking the first, this one, uh, this image, and I'll be slicing it and overwriting it and saving it to show how it's saved. Like, mm, also, yeah, one more thing I want to mention. So, when the editing which you mentioned could be the like modifying the original file, FITS file itself, or creating a new file. So, what I know from what I've learned is modifying original FITS file itself is kind of risky and also not really recommended. But what we do is save our tweaks in a new file itself. So what I covered in 10th section is creating a new file to register the changes which we have made previously. Like, so that's a like most basic level of editing I have done to this FITS file. The edit which you were talking about is kind of like goes into more advanced steps. That's why I'm not covering it today. Because obviously there's day 4 up to 7, right? Mm. Okay, so that's the basic editing and saving. The function which we use for it is write to, as you can see. Mm, it wasn't really that hard. Uh, so that's about it, I guess. Yeah, right. Also, when you are done with your uh, its observation or editing or whatever, be sure to close it to ensure your kernel doesn't crashes, right? Because it can overflow your kernel with the amount of data like usual FITS file contained, the actual FITS file, not the example one which I took. This one is really small, but the actual FITS file can overflow your kernel, which is memory inefficient. Mhm. All right, time for questions. Hmm, it went way too fast, so I think I should cover a bit more. Mm. Mm. We do have one questions. Okay. So with WCS, can we convert to other coordinate system? Yeah. Yeah, we can. I think so. Mm, Galactic uses parameters. Okay. I'm not sure about the galactic though. I'm not familiar with that system actually. And maybe you guys have done it, but I haven't. But yeah, we do. We can obviously change our coordinate system. Next is a notebook for, I guess, an example. Mm, okay, right. So there's one notebook. Sorry, there's one FITS file which I'm gonna show you for analysis. Okay. Mm, all right. So first, obviously, we import the libraries and all that. Next is opening FITS file. I mean, I already explained these functions. Still, I'll cover that. So I'll import this that FITS file. All right. Open it and fetch the information of it. What I can see is there's only one row, the primary row, which means this specific FITS file, which I have chosen, only contains the image data, not any other data. So that's all we'll be getting. So what we can deduct from this FITS file is just visualization and not any other kind of data. All right. So next, obviously, we'll inspect the header. Okay, yeah. Since it is a synthetic data, it does not contain any actual information about what it observed, what telescope was used, what was the observation date, because obviously we generated it ourselves. And how we generated it, you can look at the code. It like kind of uses the logic of noise mapping. We generate random numbers and assign those values in FITS file. Okay. Right. So it does not contain the actual information about these things, and also it won't contain history as well, because obviously nothing was done to it before. Okay. Next, we extract the image data. As we can see, the dimension for the image is 256 pixels into 256 pixels in both x and y axis. Right. Mm, as I mentioned, we need to see, like, kind of get the idea of the brightness of different bodies, the brightest object, the faintest object, the average brightness of the sky. Right. So we'll calculate the basic statistics of the image, and we linearly scale it first to see the difference after the logarithmic scaling. By the way, if you have any questions about the functions and parameters, please do ask. I'm not explaining the functions and parameters because it was covered yesterday, right? You can explain those functions as well, what we are doing, what values are we passing. There would be syntax error and a lot of doubts if you guys aren't able to understand something. Right, I'll lay this question here. You can drop your questions about the syntax, right? So first we plotted a graph for its linear scaling. Width is very faint, not clear, obviously. Then we do logarithmic scaling. All this is for just visualization, right? Because there's only image data in this specific FITS file, right? So after logarithmic scaling, it's much more clear than before. Then we plot where it is. Then we close it. I guess I'm not sure if I can explain any more intuition beside these. If you have any suggestion, please. Yes, I think you were saying something. I mean, for Fitz file handling, that I think I've covered everything besides the deep down theories, which will take a lot of time. But for the coding aspects, I think I have covered most of it, even though it went too fast. Basically, what we have to do, you can see this in one. ah, wait. Right. So I'll again summarize the basics of its file handling. So, I mean, these are the usual steps which you have to do. You can even use this file as a template to do the basic work of visualization. So obviously, first you import libraries, then open the FITS file, then inspect the FITS file, inspect the header, inspect the image data. We do some basic statistics to get the idea of what's in the image. Plot it. There's logarithmic scale to visualize it better in a better way. Then you coordinate at like you plot a WCS of it. That's it. If there's something more which I can cover, please do suggest. Mm, okay, so like if you guys don't really have any questions, then I mean you have time obviously whole day. You can ask questions later as well. So we can end our meeting, right?